Welcome to springlib.
Let's fix x and let's assume that y is the floor of root 2x plus 1/2. By definition of floor, y must be an integer such that y is lower or equal than root of 2x plus 1/2 and is lower than 1 plus 1. So now we can subtract minus 1/2 to every term and square everything. And finally divide by 2. So if we know that y is the floor of root 2x plus 1/2, we know that x must satisfy this inequality here. So all the values that are between 1 minus 1/2 squared half and 1 plus 1/2 squared half are such that floor of root 2x plus 1/2 is exactly y. Now we ask ourselves, what integer numbers can be between m minus 1/2 squared half and m plus 1/2 squared half? It's useful to think of the distance between these two bounds. So let's call L the distance between these two numbers. Of course, L is given by the last one minus the first one. Now this is just a bit of algebra. We explicitly write the square. So it is m squared plus 1/4 plus m minus m squared plus 1/4 minus m. And after simplifying everything, we just left with m, which means that there are exactly m different numbers, let's call them n, such that root 2 of n plus 1/2, you take the floor and that's exactly m. And of course, those are the first m integers coming after m minus 1 squared half. But we observe that m minus 1/2 squared half is not an integer, because if we take m to be integer, then m minus 1/2 is half an integer, and when you square and divide, you still get not an integer. So the situation is, let's write our line of real numbers. Let's start with 0 here, and then we have 1 minus 1/2 squared divided by 2, which is exactly 1/16, so that's 0.1 something. So that falls there, in between 0 and 1. Then we have the next one, which is 2 minus 1/2 squared divided by 2, which is 1.1 something. And then we have the integer numbers 2 and 3. And then we have the next bound 3 minus 1/2 squared divided by 2, which is 3.1 something. Then there are 4, 5, and then there we have 4 minus 1/2 squared divided by 2. And we observe that the distance between the first and the second bound in red there is exactly 1. Then the distance between the second and the third bound is exactly 2. Then we have a distance of 3, and so forth. And so we can write this graph. So let's write m on a table, and let's write on the other side all the possible integers n, such that the floor of 2n plus 1/2 is exactly m. And by our analysis, we know that if m is 1, then the only possible n that can work is 1. That's the first integer after 1 minus 1/2 squared divided by 2. Then if m is equal to 2, we have the following integers. We have 2 and 3. And then again, if m is 3, then the possible n's are 4, 5, and 6. If m is 4, we have 7, 8, 9, and 10, and so forth. Another way of seeing this is that a of 1 must be 1. So we have a of n, which is floor of root 2n plus 1/2. So a of 1 must be 1. Then a of 2, we see from the table, must be 2. And a3 must be 2 as well. And then we have a4, which must be 3, a5, which must be 3, a6, which must be 3, and so forth, which finishes the proof.